Hello fellow problem solvers. So today we're going to be doing the problem 1 from the 2025 IMO, and I suggest you try this problem out for a minimum of 15 minutes, 30 minutes, ideally an hour to an hour and a half, not more than 4.5 hours. If you'd like to go along with us, do give this a try, read the problem. I'll put it up right now for the next 5 minutes. Okay, let us begin. Okay, so what do we have here? So now that you read the problem, what is the first thing you notice we have? So the first thing to do in a problem like this is like, for me, when I read this, I was like confused. Sunny lines? What's the condition? What's happening? And like the first sort of thing to do to make sure you understand it is, okay, we have these two conditions. So for all a and b that are positive integers less than or their sum less than or equal to n plus 1, the point lies on at least one of n lines, and exactly k of these n lines are sunny. Okay, so let's see what's really happening here. So let's say we have the xy coordinate system here, okay? Now we have points, say, for n equals 3. So what is a principle I keep coming back to again and again and again as we're solving different problems? That is the principle of play around with the problem. And I'm going to keep hammering it on, and now you're just going to see in problem number 1, it's very, very much alive. So play around with small cases here. Now, what do we see here? Okay, so for n equals 3, what do we not want? We sort of, it's not that we don't want it necessarily, but we're trying to see how can we sort of get free lines such that we can control the number of these lines that are parallel to these red ones, right? So where x plus y is 0, that's this line, parallel to the y coordinate, y-axis, and parallel to the x-axis. So that's what we want to know. Now, can we first and foremost do this with 0 sunny lines? Well, for n equals 3, yes, we absolutely can. We just do this 1, 2, 3, ta-da, and we're done. I mean, we could do it in many ways. We could do it like 1, 2, 3, ta-da, we are done. So n is equal to 3, k equals 0 works. Now, what is a sunny line? So not parallel to any one of these y-axes. So can we have exactly one sunny line and 3 lines that go over these? Again, it's a matter of, okay, I can just do 1, 2, and 3. We just do one line, we tilt it a bit, and now we have k is equal to 1. Can we do now, so k equals 1 works. What about k is equal to 2? So for 2, it means we want one of these non-sunny lines. So maybe so whichever one we choose, whether we choose this one, whether we choose this line. I mean, actually, so whether we choose this, or this, it's going to give us the same shape, just moved. That's something to notice. Again, you're noticing small things. Another principle I said before the IMO, and I'm going to say it again, start simply before moving on to complexity. So one option is this, basically. Another option is this. And a third option, which I don't think makes a lot of sense, is just this. Okay, so let's start off with this for 2. So if we do this, then 2 of these points need to be on the same line, but no matter how we do it, the line is going to be, the line that has 2 points on it is not going to be sunny. So if we do this, then we have 3 points down here. So we have 2 lines, and we have a total of 4 points. So whatever we do, we can only connect this point with one of these, and the other 2 need to be on the same line. So that's not going to work out. And of course, finally, like just doing this, we have 5 points. I mean, these 3 points, 2 of them need to be on the same line because there's 2 lines, and it doesn't work out. So we see that really for k is equal to 2 is not going to work. And for k equals 3, that's really saying, okay, I have 0 of these parallel lines. So let's see what can we do there. So let's maybe connect these 2, we connect these 2 and these 2, and there you go. So k equals 3 works. So for n equals 3, we have k is equal to 0, 1, and 3. Now, I invite you here, if you haven't done so already, for n equals 4, do pause for about 10 minutes and try to play around with it and see what are the possible k's for n equals 4, okay? Pause now, and now let's continue with the problem. So what do we have? We have that, okay, can I do k 0, 1, and 3? That's my first question for you. And what you notice is once you're playing around a bit, it's like, wait, I can just like do this one blue line, and I immediately get, okay, a sub problem here. So I immediately get 0, 1, and 3, which basically says, okay, like I can just do this for any n. So for any single n, I'll be able to get k is equal to 0, 1, 2, or 3. Why? I'll just do all of these lines, and then I'll do the subproblem. So if we get a k for smaller n that works, then works for all larger n. And that's pretty cool. So now that we've seen that for 4, we're going to have 0, 1, and 3, can we see what's going to happen with 2? And now you can play around a bit. You see, okay, I'm going to have 2 parallel lines. It has to be like a line like this. And now I need to see how I can connect points in a non-parallel way. Maybe I connect these two, but then I can't. I'm left with 3 points like this. And you keep seeing that you cannot do anything. And the major idea here comes with you noticing that, well, what I've done previously is I've looked at these points that are on the boundary. Okay, if there's a line that's connecting like 4 points on the boundary, then you have n equals 3 basically, and you have the same k. Now, what you do realize is that also like, so if I'm going to get something else for anything other than 0, 1, and 3, I'm going to need to break this somehow. I'm going to need to make it so that there's no line that's only like this goes through all of these 4 points, all of these 4 points, or all of these 4 points. There cannot be such a line for 4. Okay? For us getting k is equal to 2. Because otherwise we are at a smaller problem. We are at a problem with n is 3, and we know that we can only get this. Right? So that's not going to help us. And again, like if this isn't making the most sense for you, then it's a good idea to just like rewind for a minute and then pause and try to understand how, like what k really is, because that's, I think, the hardest thing to really wrap your head around when you're starting off with the problem. But okay, let's go back to the problem. So what do we have here? We now know that, wait a second, we have how many? 3 plus 3 plus 3, 9 points here. And we're going to have 4 lines in total. So to cover all of this, you're going to need one line. We'll need to have at least 9 over 4, the ceiling of 9 over 4, which is what? Which is 3 points. So if you don't get up this line, or this line, or this line, you can't get 3 points. That's a contradiction. So this means for us to get condition 1 satisfied, for all positive integers a and b, such that a plus b is less than or equal to n plus 1, the point a, b lies on at least one of the lines. For us to get that satisfied, with just these points on the boundaries, we need a line that goes through the boundary. That goes through like 3 points on the boundary. It cannot go through 2 points from 2 points from one side and not a third one. If you need it, so like we could say like there's 3 of these. How do we call them? 3 of these. Call these points on vertical 1, vertical 2, vertical 3. I don't even know how to call them. Line 1, line 2, line 3. And you could say, well, we need a point from line 1, one from line 2, and one from line 3. But there's no way those form a line. So that would be a contradiction. That would be like why we need a line here. And now I invite you here. After we've played using simple ideas for n equals 3, n equals 4, you can maybe look at n equals 5 as well. But now's the time for you to generalize this problem and finish it up. And now what I'm going to do is just that. So what is the idea? The idea is, well, we're going to prove via induction that only k is equal to 0, 1, and 3 works. Okay? So let's assume this is true all the way till n minus 1. We know it's true for 3, we know it's true for 4. Let's say it's all true till n minus 1. Our claim is that for condition B to be satisfied, there's going to be at least one non-sunny line that covers this boundary, either the boundary of these points, or you could even say the convex hull of these points if you want to be more precise geometrically. We're going to prove that. Assume the contrary. Assume none of these lines is active, is one of the lines that are in our configuration. Well, we have free and minus 3 points here. Each one of the, and we know that n is greater than or equal to 5. So there's a total of n lines. These n lines, on average, have this many of these points on the convex hull. So on average, each line has free minus 3 over n points on the convex hull, which means this thing is greater than 2. Which means what? Well, that means that there is one line which has 3 points from the convex hull. Now, how can it have 3 points from the convex hull? Well, if it doesn't have this, if it doesn't have if it's not one of these lines, then it's basically impossible. And that then says, okay, so one of these lines actually needs to be in our configuration, either this one, or this one, or the other one. So either line 1 being this, line 2 being this parallel of this x plus y is 0, or line 3. So one of these 3 lines needs to be in the configuration, and then we notice, okay, once you add that one, we are done basically by induction. And that solves the problem. Now, looking back at the problem, what I'd say here is like the major idea, what are the major learnings from this problem? So number 1 is, as always, what you do need to do is like play with small numbers. So you play with n equals 3 to like figure out, okay, the configurations that have, what's it called, 0, actually that have 3 of these things, that have 3 of these sunny lines, that has exactly 1 sunny line, and that has 0 sunny lines. And then you notice, okay, from 4, what do I have? 5, what do I have? And then you can generalize from there. I think after you get to 5 or 6, you're down to generalize very quickly. But that's like the importance, especially on the sort of easier problems, of play with smaller cases. And then I'd say number 2 is simple ideas before complex ones, right? I mean, we could have done something along the lines of, well, okay, we have points. How many points do we have in total? Well, in total, we're going to have n times n plus 1 over 2 points. I mean, even this is still simple, but I think complexity would have been, what are the angles of these lines, or what are the, we could have been looking at, say the lines are characterized by AIX plus BI equals Y. Say this is the characterization of all of these, what's it called, lines. And we're trying to figure out, okay, what are the x's going to be such that all of these things are covered, right? That would have been a much, it would have been a more complex way to solve it from the get-go. But it's okay if this did not work, if these ideas did not work, like the convex hull idea, just looking at these little lines, to then, okay, let's actually try to write it down algebraically, what we can do there. To do that sort of thing is fine, but it's after you've done the simple sort of, okay, let me just play with some small cases, let me see, okay, if I put a line here, I put a line there, what's really happening? And I'd say like those are the 2 main learning lessons. Start with simple ideas before going on to more complex ones, and to play. And from there on, you generalize, you notice simple things, and you generalize from there. So this finishes up our problem on day 1, and as always, thanks for problem solving.